Today we are going to study reflection in 2D. Before diving deeper into the reflection phenomena, first look some of the salient features of reflection which you observe in day-to-day lives. Reflection basically creates mirror images. We all know that by our day-to-day observations. Now let we try to look into this phenomena from geometric point of view. Say this is your two-dimensional space which you usually define in terms of x-axis and y-axis. Now assume that in the first quadrant of the space you have a triangle ABC. Here. Now, can you imagine what will happen if you reflect this triangle ABC with respect to the y-axis? Just think for a few moments and try to figure out the answer. If you reflect this triangle ABC with respect to y-axis, then you will have the reflected image of this triangle into the second quadrant of this 2D space somewhere here, and this is going to be your reflected image. If you carefully observe, the reflected triangle A-B-C- is basically the mirror image of the original triangle. It is the mirror image of the original triangle. And if you follow further, then this distance is equal to this distance. The horizontal distance from point A to the y-axis is equal to the horizontal distance between A' and y-axis, and the horizontal distance between the point C, let me do it with another color, is equal to the horizontal distance between point C' and y-axis. So this is reflection with respect to y-axis, where you get a mirror object of the original thing onto the other side of the y-axis. Now let we do the same reflection thing with respect to x-axis and try to follow what phenomenon occurs here. Again, let we first define our two-dimensional space in terms of x-axis and in terms of y-axis, and let we draw our triangle A, B and C here. And now we will try to do the reflection with respect to x-axis. Reflect triangle ABC with respect to x-axis, and let me try to observe what will follow. If you follow the previous discussion, then you will be able to observe that after reflection, the distance in between point B and the reflection of point B must be equal. So you will have your point B somewhere here. Similarly, for point C, the distance between it and x-axis is going to be equal to the distance between the reflected point and the x-axis. So C dash is going to be somewhere here. Similarly, if you reflect point A with respect to x-axis, the distance between point A and x-axis is going to be the distance between the reflected point of A, which is going to be A dash, and x-axis are going to be equal. This distance and this distance are going to be equal. Now let me join the three reflected points, and if you join the three reflected points, you will get the entire reflected object. In this case also, you can observe that you actually get a mirror image after reflection. So let we now dive deeper into the reflection phenomena. So from the discussion what we have done until now, we can conclude two things. Number one, we get mirror image in reflection. And point two, if you go back to the previous two diagrams, you can see that for both the cases, reflection was performed with respect to some line. For example, in the first case, the reflection was done with respect to y-axis, which essentially is a line. Y-axis itself is a line. Similarly, in the second example, what followed was that the reflection has been performed with respect to x-axis. Once again, x-axis itself is a line. So we can conclude that in 2 dimensions, reflection is performed with respect to some line. Now, in 2-dimensional space, x-axis and y-axis are the lines which are always defined by default. However, reflection don't always have to be performed with respect to x-axis and y-axis only. It can be performed with respect to any line. Say this is your line L and you want to reflect point A with respect to this line L. So just what you can do, you can hold this entire piece of paper by this line L, and if you do this folding, you will get a mirror image of this point A somewhere here. So this is your reflected point of A with respect to this line L. This we will go see later on during this module, but at first let we do some deeper dive into this reflection phenomena. Say this is your x-axis and this is your y-axis, and here is your point xy, which you will reflect now with respect to y-axis. So as we have discussed before, you will get your reflected point somewhere here, x dash y dash. Now if you can observe, x dash is going to be equal to minus x and y dash is going to be equal to y, and this was reflection with respect to y axis. And so if you convert these two equations into matrix form, you will get something like x dash y dash equals to minus 1 0 0 1 multiplied with matrix xy. So this can be your reflection matrix with respect to y-axis. Now try to convert this thing into homogeneous system. So you have to introduce an extra 1. Now your equations become x dash equals to minus x, y dash equals to y, 1 equals to 1, and this implies x dash y dash 1 equals to minus 1 0 0 0 minus 0 1 0 0 0 1 multiplied with x, y, and 1, and this is your generalized reflection matrix with respect to y axis. Now let us try to do reflection with respect to x-axis. Say you have your point xy somewhere here. Now you want to reflect it with respect to x-axis. So what you do, you calculate the vertical distance from point xy to x-axis, which is basically y, and so the reflected point you will get at a distance equal to y but below y-axis somewhere here, x dash y dash, and this distance is basically minus y in negative y direction. So what follows is, now x dash is equal to x and y dash equals to minus y. If you convert these two equations into matrix form, you get something like x dash y dash vector equals to 1 0 0 minus 1 multiplied with x y. So this is your reflection matrix with respect to x-axis. Now try to convert this equation into homogeneous form. So x dash equals to x, y dash equals to minus y, 1 equals to 1. And if you convert this into matrix form, you get x dash y dash 1 equals to 1 0 0 0 minus 1 0 0 0 1 multiplied with x, y, and 1. So this is your reflection matrix with respect to x-axis. So in a nutshell, what happens is that reflection matrix reflection matrix with respect to x-axis goes like 1 0 0 0 minus 1 0 0 0 1, and reflection matrix with respect to y-axis goes like minus 1 0 0 0 1 0 0 0 1. So this was the basic derivation of reflection matrices along x-axis and y-axis. Now let we try to apply this sum towards real problems. Say you have a point 4 2 which you want to reflect with respect to x-axis. What will be the coordinates of resulting point? So just have a look at the problem once again. You have a point 4 2 which you want to reflect with respect to x-axis. What will be the coordinates of resulting point? So as per the problem statement, x is 4 and y is 2. You are being told to reflect this point xy with respect to x-axis. So your reflection matrix will be 1 0 0 0 minus 1 0 0 0 1, and your x dash y dash, that means points after reflection, you can get by multiplying t-ref with xy1. So it will go like x dash y dash 1 equals to 1 0 0 0 minus 1 0 0 0 1 multiplied with 4 2 1. So x dash becomes 1 multiplied with 4 plus 0 multiplied with 2 plus 0 multiplied with 1 equals to 4. Y dash is 4 multiplied with 0 minus 1 multiplied with 2 plus 0 multiplied with 1 equals to minus 2. So x dash y dash equals to 4 minus 2. So you are going to get your resulting point at 4 minus 2. So that was all about reflection in 2D. Hope you have learned something